So we come to the conclusion now of the Michelson Morley experiment. We need to take the analysis we've been doing with our airplane example and apply to the actual experiment that Michelson and Morley did in the later 1880s. And so here's the setup they used. They were using light, of course. So they had a light beam coming in. So in this case, the light beam is taking the place of our airplane previously. And we've got the ether wind. We're just imagining it's coming down here. This whole apparatus actually is they put it on a big sandstone slab. And so we're looking down at the top of the apparatus, as it were. And so they're assuming there's an ether wind coming from this direction here. This light beam comes in, and there's a half-silvered mirror here. And what a half-silvered mirror does means that some of the light, if it hits it, will bounce off that way, and some of it will actually travel through the mirror. And so the light that bounces off goes up to this mirror, bounces off that, comes back down to the half-silvered mirror, and then some of that will actually bounce back the other way, but some of it will go through to the detector down here. So that's path A, off the half-silvered mirror, up to this full mirror, back down again through the half-silvered mirror and to the detector. And then path B, which is going crossways in comparison to the ether wind that's assumed to be there, goes through the half-silvered mirror, bounces off this full mirror, back to the half-silvered mirror. Some of it does go through, just straight through, but some of it will bounce off the half-silvered mirror and end up at the detector. So essentially what we're doing here is we're taking a light beam, we're splitting it into two. One half of the beam takes path A and then back to the detector, and the other half of the beam takes path B to the detector. And in this orientation, path A has the headwind and then tailwind, and path B has the crosswind. And other than that, the analysis is exactly the same in terms of how we did it with our airplane example with the tailwind, headwind, and then the crosswind. So the path A time, which is the tailwind, headwind, tailwind example, remember it was 2D over v sub plane, but here the light is taking the place of the plane. So we have c, the speed of light, times 1 over 1 minus vw squared, the velocity of the ether wind, and we'll figure out what that might be in a second, divided by c squared again. And then the path b time, which is the crosswind time, 2d over c, 1 over the square root of 1 minus vw squared over c squared, where d here is the distance to the mirrors, from the half-silver mirror to that mirror, and that one as well. What would be the velocity of the ether wind? Well, it turns out that if we're assuming that we're doing this and the Earth is rotating around the sun, obviously there's an effect of really the rotation, 24-hour rotation of the Earth, and then the revolution of the Earth around the sun. The major effect of that is actually the Earth going around the sun because it's much faster. At the surface of the Earth, we're traveling, well, the number I know is about 1,000 miles an hour as the Earth rotates. But in terms of traveling through the solar system, or around the sun, as it were, it's about 30,000 meters per second, so much faster. So that traveling around the sun is the main velocity effect that's going on. So the idea is as we travel around the sun, as the Earth travels around the sun, we'll be experiencing an ether wind. We're traveling through the ether just like riding a bicycle through a still air. You feel the breeze in your face. So this number here for v sub w, about 30,000 meters per second. And just for comparison, speed of light, though, is still much, much greater than that. It's 300 million meters per second, which is about 10,000 times faster than the speed of the supposed ether wind here. So path A time, path B time, the tailwind, headwind, and the crosswind time. And what we'd like to do is just figure out, as you can see here, what's the difference in travel times? What's the effect of the ether wind on the light? And again, this goes back to some of our analysis, qualitative analysis of just how waves work. That if a wave is in a medium, and the assumption here is that light waves, the medium of light waves is the ether, and if that is moving, then that affects the speed of the light that we would measure. So that we should see a difference here. So that one path should be a difference in travel time compared to the other path when it gets to the detector here. And we'd like to know, exactly what that difference might be for representative numbers here with the speed of light and the speed of the ether wind there. Now, we could just plug in some numbers here and you get an answer, but we'd like to get it in a little nicer form than that, and we'll use something we mentioned in the first video clip on the Michelson Morley effect here. So let's just see if we can simplify it slightly. So we'll say, and it's also a good example of what physicists often do in situations like this. So we'll say we still have 2d over c here, and what I did here, of course, is just this minus this. They have the 2d over c factor in each case, so I pull that out. You have just that, then minus that. Doesn't really matter which way you subtract them. 2d over c. I just want to rewrite this in here for a second, just slightly different notation that we talked about before in terms of the exponential notation. This 1 over something is that something to the minus 1 power. So let's write that. So this becomes 1 minus VW squared over c squared to the minus 1 power. So we haven't really done any math there, just changed our notation. And then minus the second term, 1 minus VW squared over c squared to the 1/2 power, and the denominator means the same thing to the minus 1/2 power if we write it like this. 1 minus VW squared over c squared to the minus 1/2 power. Okay, so just change the notation there. And now, again, to get room, we're going to erase this. So hopefully you've been taking notes or pause it. It's really the same equations we had before. We'll leave the diagram up here for reference because we'll be using that again in a little bit. So difference in travel times now is, so we'll bring this up here, is going to equal 2d over c. Have that still. Now, here's where we use a mathematical technique that physicists love to use when they can, and that is, remember we talked about the binomial expansion, and just to remind you what that was, this was from the first video clip on the Michelson Morley experiment. When we have something like this, say 1 plus x to the n, if x is much smaller than 1, then we can write this as approximately equal to 1 plus nx. Okay? And note, this is why I rewrote this here. This is the form we have. I have something, essentially, x in this case is the VW squared over c squared. And if I have a minus sign here, this just becomes a minus there. So either way works. So I've got 1 minus something to the negative 1 power. So in this case, n is negative 1. X is the VW squared over c squared, and then just a minus sign instead. So I can do this. 1 minus x to the n is approximately equal to 1 minus nx, where it can be positive or negative. So, well, is this thing here much less than 1? This is only if, just to remind, if x is much less than 1. There. Well, think about this a minute. We mentioned that the supposed velocity of the ether wind, 30,000 meters per second. Velocity of light, 300 million meters per second. That's a 10,000-fold difference between the two, plus they're squared here. So really the difference is 10,000 squared, which is about 100 million times, if I did that right in my head. 10,000, 10 to the 4th, for those of you who do things like that. Square it, you get 10 to the 8th, which is about 100 million times. So this is a very small number when you do the VW squared over c squared. And therefore, yes, we can use the binomial expansion as an approximation. It works in this case. So what do I have here? For this one, again, using binomial expansion, I've got, we'll write it out here, so I've got 1 minus, okay, then what's n? N is negative 1 here. So it's negative 1 times VW squared over c squared. Okay, so that is this part here, just applying the binomial expansion there, the first couple terms of it actually, the first two terms. Okay, and I have to erase that to get a little room here. And then we're going to apply it to this term as well. So I took this term, that's what this is, and then I've got a minus here. So just to be clear, we'll get a lot of parentheses going on here. Minus then 1 minus negative 1/2, because that's the n value, the exponent value, times VW squared over c squared. We've got one more parenthesis there to fill everything out. Okay? Now it looks a little messy, but look, it gets very simple very quickly. We still have the 2d over c on the outside, so that's fine. Now I've got 1 minus a negative 1 times that. That's just 1 plus that. So this becomes 1 plus VW squared over c squared. Over here I've got minus, and we'll do it step by step here, 1 plus 1/2. Because minus times minus, positive, 1/2. VW squared over c squared. And we're almost there. Equals 2d over c. So what have I got here? I've got 1 plus VW squared over c squared minus 1 minus 1/2 VW c squared, right? If I've got minus something in parentheses, it just becomes something like this. So this then becomes minus 1 minus that. So a little writing there. And now I've got a 1 minus 1, 0, and I've got a VW squared over c squared minus 1/2 VW squared over c squared. So this just becomes 2d over c. The 1's disappear. I'm left with 1/2 VW squared over c squared. The 2's cancel here. And finally, I'm left with d over c times VW squared over c squared. And the reason we went through it partly is just to show you that physicists love to do these types of things, to get it down to a much simpler form so that, assuming the approximation is correct, that we can use the binomial expansion in this case, and it is. So what is this number? Remember, this is the difference in time between the two paths here, path A and path B, in terms of the recombined light beams. They end up back in the detector here. One takes a little bit longer than the other, one in general. And this is a difference in time between them. Well, what would you, if you actually put in some numbers here, what would you get? In the most famous version of the Michelson Morley experiment, D was 11 meters. Okay? 11 meters, that's about more than 30 feet, 33, 35 feet, something like that. Just to give you an idea, if you think in terms of feet rather than meters. But 11 meters, that's pretty big. And you might ask, did they really have a table that big? In actual fact, in the experiment, they had a big sandstone slab that was set on oil. So they have a very nice solid foundation, free of vibration, things like that. There's sort of an oil bath it sat in. And they actually had some other mirrors here. So they bounced the beam back and forth a few times in each way so that they could get a longer path length without having to have a huge table. So D's 11 meters. C, speed of light, 300 millimeters per second. We mentioned VW, 30,000 meters per second. Again, speed of light, same thing as before. You work all this out, and you get an answer that is approximately equal to, say, well, we won't use 4. We'll use, it's actually closer to 3.67 times 10 to the minus 16, I think it is. Got my numbers right there. Minus 16, yeah, that looks right. Seconds. Yeah. 3.67 times 10 to the minus 16 seconds. That clearly is a very short time interval. And there was no way Michelson and Morley could measure a time difference of the two light beams arriving at the detector that precisely. And you might ask, for those of you who are really thinking through this, you might say, well, also, what about the assumption that we're using D here, 11 meters? How do we know it's exactly the same in each path? And the actual answer is we don't, but they used an ingenious method. What they did is they would do one measurement, and of course you assume that either wind is coming from a certain direction. You don't quite know, perhaps, but you can figure out in terms of the rotation of the Earth at any given time, where they are, what time of day it is, and so on and so forth, and the direction of the Earth around the sun. So you can get a pretty good idea where the ether wind should be coming from. So they do one measurement like this, and then they just rotate their whole table, their sandstone table, 90 degrees, this big slab with all the equipment on it, 90 degrees, and then do the measurement again. And it turns out, we won't go through the analysis of that, it turns out if you do that, then this time difference is doubled. So instead of 3.67, we'll just say it's about 7 times 10 to the minus 16 seconds. Again, very small. But that's how you get rid of any dependence on the actual distance there. And so you might say, well, great, so what did they do? You know, if you can't measure something like that. Well, Michelson was a brilliant inventor and experimental physicist, and later won the Nobel Prize for it. And he developed techniques using interference techniques, using interference phenomena of light waves. And that's why, a few video clips ago, we talked about constructive and destructive interference between two waves. And without revisiting all that, here's the basic idea of what happens. The two light beams take their different paths. They recombine back here at the detector. If there's been no path difference at all, no time difference, they both arrive back exactly at the same instant, then you can imagine the light beams coming in here. Let's use orange. Here come the light beams back into the detector here. And here comes the other one in. And you have a case of constructive interference. So you get a certain pattern of light patches, bright patches where the peaks are, and then dark patches where the troughs are of the wave. So you get a distinctive pattern there. Well, it turns out that the light they were using was sodium light. And for sodium light, let's erase some of our analysis here now. We don't need this. We've got our final answer down here. So here's our final answer for delta T, the time difference there, and 7 times 10 to the minus 16 seconds. Turns out, so they use, as I mentioned, sodium light, which is a very nice, bright source of light that they could get into a beam and send into their apparatus like that. And just give you some numbers here. You don't have to memorize these or anything. But sodium light, turns out, remember we used the symbol lambda for wavelength? Sodium light has a wavelength of 589 nanometers, billionths of a meter. So again, very short distance there. And another equation we mentioned when we were talking about light, we used frequency. We used F for frequency here. So F, the frequency of light, remember, is c over lambda. So given 589 nanometers, billionths of a meter, and the speed of light, we could figure out what frequency that sodium light represents. But also, we know the period, which is the time between the peaks of our waves here, is 1 over the frequency, which is lambda over c. And that's really what we're most interested here in. If you do this calculation, you will find the period for sodium is about 2 times 10 to the minus 15 seconds. Again, still a very small amount, difference between the peaks in this bright sodium light, sort of yellowish light. And so 2 times 10 to the minus 15th seconds. How is that significant for us? Because look at this. We say, the experimental analysis says that the time difference, if there's this ether wind blowing here, there's a cross wind and then a tailwind headwind case, the time difference is 7 times 10 to the minus 16 seconds. Really, really small. But compared to the period, not so small. In other words, if you do this, if you say, okay, I've got my time difference of 7 times 10 to the minus 16th seconds, very small, but in terms of the one period, the time between two peaks, so let's divide it by that, 2 times 10 to the minus 15th seconds, And if you get out your calculators or just do the math there, you find this is about 0.37. What does that mean? Well, what it means is that what will happen is, with that time difference, the two paths of the light here, one of them will be shifted by about a third of a period. Okay, so instead of coming in exactly in line with each other again, one of them, this peak will get shifted over by a third. So all these peaks will get shifted over by a third. They will no longer be aligned with each other. You'll get a different interference effect at the detector. Okay? So that if the ether wind is blowing, or really if Earth is moving through the ether, then you should see this interference effect. There should be a change in the so-called fringe pattern, as it is. We talk about the constructive and destructive interference fringes that they'll see. And it should be relatively, in terms of the apparatus they had, not too difficult to see. 1/3 of a period meant that actually the light and dark areas would shift slightly by about a third. And again, with the apparatus they're using, should in principle be pretty easy to see. So what did they find? They found, when they did this, that the observed shift, they did it a number of times, different orientations, different times of the year, and so on and so forth. The observed shift, I think, was about 0.005. In terms of the experimental uncertainties they were dealing with. The observed shift could not be greater than this. It might even be less than that. And so this is what's known as the famous null result. The famous null result of the Michelson Morley experiment, because they didn't see the effect of the ether wind. And physicists, many of them, they just didn't know what to do. They said, how can this be? Where is the ether wind? Light is a wave. We know that. That's well confirmed theoretically and experimentally. And we know that a wave has to have a medium that it travels through, a disturbance through some medium. We assume it's the ether. We give the name ether to that medium. We're not quite sure exactly how it's put together, what it consists of, and how it works, and so on and so forth. But it should be there. And yet we're not seeing any effect of it. So one possible explanation would be, remember the whole idea here is the Earth is revolving around the sun and moving through the ether that way. Well, what if at the surface of the Earth, maybe the ether gets sort of dragged along just by the matter of the Earth, or who knows, maybe the atmosphere is involved as well, so that you're sort of on the surface of the Earth, we're in a pocket. We're protected from the ether wind. So in fact, on the surface of the Earth, there is no ether wind blowing. And that could be a plausible explanation. Obviously, it would require some experimentation, some investigation to see if that actually made sense or not. And as it turns out, the reason they didn't immediately turn to that is there were other experimental results that showed that you could not have this so-called ether drag effect, that the Earth did not drag the ether along with it. And in fact, that's what we'll be working on in our next video clip. It's the so-called stellar aberration effect. So the upshot of it is, and we're not going to go into all the details we did on the Michelson Morley experiment in terms of actually working through some of the math here. But conceptually, it's fairly straightforward. It's really sort of that airplane effect, crosswind versus tailwind, headwind. Michelson Morley had to use, as I said, some sort of path-breaking experimental techniques to actually measure something that's in principle this small, a time difference that small, but by using the interference effects involved, they actually could in principle see the result, and yet they saw essentially nothing. And later on we'll talk about what impact did this have on Einstein himself. Did he use this as a starting point for his theory of special relativity, or maybe some other things were equally as important or maybe even more important to his thinking. But before we get there, next video clip, we'll talk about the stellar aberration effect, just the idea behind it. So again, it sets up a huge conundrum, a huge puzzle for physicists. They couldn't see the ether. They couldn't see the effect of the ether in the Michelson-Morley experiment. Stellar aberration said, ether drag can't work either, so what do you do with the ether? How do you solve a problem like like the ether. And so that's what in the second half, really actually later decades of the 19th century, they were really puzzling over.